Hi guys, and this is going to be a very interesting video. This is going to be a little bit of a tangent, but this is going to kind of go over some very interesting math. It's going to cover probability, it's going to cover combinatorics, and especially the choose function, or choosing, like as in choosing a number of objects, how many ways there are to choose a number of objects, given that there are, n total objects. So like the n choose k. So we're going to kind of go over the kind of math that we're going to go over in this example here in kind of a fun way, and hopefully this will help us kind of remember a lot of this stuff. And hey, if you're bored during quarantine, this will probably give you something else fun to do. I certainly had a lot of fun making these materials. And I had fun learning about what this was here. So we're going to go over probability. We're going to go over combinatorics. And we're actually going to go combinatorial probability. That's actually what we're going to be doing in this one. So kind of combining both of these, it'll give you a way to solve some very cool kinds of problems out there. Plus, you'll get more familiarity with both of these concepts while learning about in my opinion, one of the coolest archaeological finds. I saw a video not too long ago on the oldest board game in our human history. Yeah, that's right. The oldest board game. Let me find. I saw a kind of a neat YouTube video on it, where this guy in the British Museum ends up playing a computer scientist at this game. I'll let you maybe look this up to see if see who won that battle. Yeah. So, with all the craziness going on today, hopefully this will be kind of a lighter thing to focus on. Hopefully y'all are staying safe. It is very unfortunate, kind of what we're going through as a country right now. I think some of the better people there are trying to heal out there, and I know that I'm talking to some of the better people out there. So thank you for your service again, let's get into one of the coolest finds that I've found in the past week. And so actually, this game, it was found, it's believed that it was played around 2500 BC. It was, the oldest version of this was a piece of wood that was still intact. It was just rotting a lot. And this that I have here is actually on the back of a pack of garlic breadsticks that are freezable, and you can put in the oven there. I feel like I'm kind of doing this game some poor justice on this. And so this is just nuts here. So just some of the history on what this is here. It's called the Royal Game of Ur. Let me write that down real quick. Royal Game of Ur. Ur is a Sumerian city. The Sumerian dynasty. All these cities, especially Ur. This is the oldest empire on the planet. Oldest empire. Here's the oldest game from there. This game, so 2500 BC. That's right after the Neolithic era, when the ice was melting around 10,000 BC. Going in the Stone Age, then Neolithic era, starting to do agriculture and discovering farming and all that. Then Bronze Age, starting to use bronze and other various metals too to create what we need. And then that goes to about 600 BC. So this game is closer, the birth of this game is closer to later Stone Age than it is to the birth of Jesus Christ. Wow. In fact, we're closer to Jesus's birth than he is to this game here. Kings and queens from Egypt may have been playing this game too. Pyramids were built around 37, about this age, about 3750 AD, I think, is when they were finally finished, or I don't remember all those details. I'm a math guy, but yeah, this game is closer to that than most notable parts in history. This game is just so old. But as I was playing it, and I gotta say, this game was a lot of fun to play. I played it with my wife. I really had a lot of fun playing this. I thought I thought it would be pretty simple, but turns out the math and the strategy is a lot more advanced than I gave it credit for at first. And so let's jump into kind of how you play this, and then we'll take a look at some probabilities here. And hey, if you have any questions, if you want to download the resources that I downloaded to print these out, print out, and play this game, I can give you a link for them. It's actually a lot of fun. I especially like how they do the dice. I thought it was really creative, even though they could have flipped some coins or had different dice. I do appreciate kind of how they liked or enjoyed using dice. So what the goal of the game is, it's a race game, and it's a lot like backgammon. Two players start opposite sides here. Here's what they do. They start here, this square, and they try and go all the way around and come off the board that way. You have to roll the exact number to get off the board. You can't be here and roll a 5 and get off the board, or 4, I guess, is the biggest number you can get. You can't roll 4 or 3 or 2. You have to roll a 1. There's a lot of really cool designs on it too. The designs are authentic Sumerian symbols. It looks like it should be something different, or looks like it should be like modern dice, but it's totally fine. And this is what I'm going to be going over is the original variation of the game. There are other variations that people played when they got bored with this or with this path. They would sometimes make up their own paths where they would start here and then they would go around and they would come around and finish off the other way, or what have you. But we're going to do like the original path there. That's the way I played. It was a lot of fun. Maybe I'll try one of the other variations as well. And so you're safe here. So this player goes this route here. The blue player goes this route. They start here. They come around and they come off the board that way. So this middle column is where most of the action happens. It's where the players' pieces interact with each other. If blue has a piece right there, red red rolls a 4, they go 1, 2, 3, 4. They knock that player that piece off. That piece has to piece off right there. Yeah, has to come off the board and start its journey over. All these symbols don't mean anything except for the 5 row spaces. The other ones are just there for decoration for whatever reason there. You land on one of those row spaces, you get another roll. So if I roll like a 1, I roll there. Oh, I get to pick up the dice and roll again. Oh, and here's how the dice work. And this is going to be key when I go over like kind of the math and the combinatorial probabilities that we're talking about. Because that's key in any game. You want to know what's the probability of each roll when you move somewhere. I don't want to move in front of someone, a certain number of spaces in front of someone, if I know that number of spaces that they need to get me out is very likely. The most likely roll is a 2. So I don't want, if I'm blue, I don't want to be here because red if red's turn comes up, they're most likely going to roll a 2 and get me out. So that plays a huge part in any strategy that involves dice. So here's how you roll. Take all 4 dice, and they're kind of big. I tried to find some kind of template where I could do it. Okay. And so here's what you do. You look at your dice. You'll notice that not every corner has a color on it. It's either white or red. White or red points. We're counting the red points that are pointing upward. That's how they counted the total for their roll. So I only have 1 that ended up pointing upward. So I have a 1. So if I'm just starting the game, I can come onto the board and go right there. Then it's the opponent's turn. It's blue's turn. Yeah, it's hard to do this and hold a phone. Luckily, they didn't have phones in their hands while trying to play this game. They had the benefit of not being distracted by the internet or Facebook while playing this game. All right. Yep. As expected, someone rolled a 2 in their first turn here. So blue can go on the board 2. And now it's red's turn again. I'm just going to go, oops. Okay, so 1 again. Red's not very lucky. Oh, I can't land on my own piece, so my only available move is that. So that's the only rule. You can't land on your own pieces. You want to get across the board here. You can land on your opponent's piece to get them out, but only in that middle column. Land on a row's piece, you get it in the free roll. So I just want to kind of share that with you, that this is like one of the coolest, games for being how old it is. It is the oldest board game that we know of right now. All right. I'm just going to get some of these pieces off here so I can kind of go dive right into the math here. And when I was calculating the probabilities playing with my wife, I realized that my assumptions were wrong, or the exact probabilities I was coming up with were wrong at first. I was thinking that I knew that a 0 and a 4 were the least likely rolls. How do I know that? Well, to get a 4, that means each one of these dice needs to come up with a red dot. That's going to be the most likely one. There's two. Each die has 2 winning points or 2 good points and 1 bad point, and 2 bad points. So the blank ones are bad points. The 2 are good points. So 50-50 shot there. They could have easily done flipping a coin, but what you could do if you wanted to play this game, I wanted to kind of see what the experience was in the original. So I knew that these were the least likely rolls. So how do I calculate the probability of rolling a 4 or 0? Let's calculate these first. It would be it would be 1/2. So my probability of success for each one would be 1/2 times a half times a half times a half times a half. So that means let's call them A, B, C, and D instead of labeling numbers there. Each one would have to come up, and each one has a probability of 1/2, or 0.5 if you like to do that. Probability, and just for reference here, probability is a number between 1 and 0 that represents our beliefs about the likelihood of an event to occur or any sort of outcome. So 1/2 on a flip of a coin describes my beliefs about the likelihood of heads occurring, and also tails. So this game is going to be a little bit wonky because the probability of success and failure for a die is the same. All right, so for 0, the probability for 0, for none of them coming up, for all of them coming up with a blank corner, is going to be the same probability. Well, first, what's this probability? 1/2, so 2 times 2. When you multiply fractions, you multiply straight across. So 1 times 1 times 1 times 1, that's just going to be a 1 on top. And then it's going to be 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 1/16. So all 4 succeed or all 4 fail. I would expect to see 1/16. And that's exactly what you see. The odds of a failure, and then a failure, and then a failure, and then another failure is also going to be 1 out of 16. That's okay. What does that leave less? Well, here's a law to keep in mind. The law of total probability. The law of total probability states that the probability of, let's say, event X plus the probability of event Y plus the probability of event Z all must add up to 1. If X, Y, and Z are the only possibilities. Law of total probability says the probabilities of each and every possibility has to add up to 1. If someone went into a coma for 50 to 60 years, and I say, what is the probability that when they wake up, that they wake up on a Saturday or a Sunday or a Monday, Tuesday, Wednesday, Thursday, or Friday? It's going to be probability of Monday is going to be 1/7. Probability of Monday is 1/7. Tuesday is 1/7. Wednesday is 1/7. Well, you add up 1/7 7 times, you'll get 1. And that's one way to check your work on any probability question. So when I calculate the probability of rolling a 1 or a 2 or a 3, that means if I add up this probability plus probability of rolling a 1, 2, 3, and 4, it must all add up to 1. That is why that's why I knew I was wrong when I was making my assumptions. I thought 2 had a 1/4. Don't ask me why. I thought it was a simple. I thought it was. Well, actually, no. I think I was under the assumption it was a half. Yeah, that was my original assumption. That's not true for this. But my assumption was a half because each one has half a chance of coming up with, and I have 4 of them. Well, okay, then I could just say, okay, it's a half for that one. Therefore, it's a half for each one of these here. Well, here's the thing. I roll 4 of them, not just 1. That means if I want to roll a 1, and let me just show what this looks like here. So what are my possibilities for rolling a 1? That's my question here. I'm going to erase that. What's my possibilities for rolling 1? It's this die A, B, C, and D. A could be the winning one. B could be the winning one. C could be the winning one, and D could be the winning one. Any one of those would be a possible answer here. So for this part, I have 4 possibilities of getting that. So here's my probability. It's going to be 1/16, same as these other ones, times 4. So in fact, it was the ones had a much higher probability of being rolled than a 0. Well, let's see. That means 3. So if I were to choose, and here's where the symmetry kind of comes into play, especially with combinatorics. With choosing 4 out of 4 is pretty straightforward. You're just choosing. There's only one way to choose 4, and that's just to choose all of them. There is one way to choose 0, and that's that you choose none of them. There are 4 ways to choose 1 out of these 4. There's 4 ways to choose which one of these die will get me my roll of 1. So that's 4. That means for 3, it's going to be 1/16. And there's going to be, so that means for 3, it's going to be a little bit reversed here. There are 3, so here's one possible way I can get my 3, or the dice will come up to give me my 3. So this would be like A, B, and C get me that. A, B, and D get me that. A, C, and D get me the 3. Or B, C, and D get me the 3. So how many ways? It's just a matter of where I put the failure die. The failure die can go in one of 4 spots. I have 4 ways of choosing failure, kind of like how in choosing 1 success. In this case, choosing 1 success is going to have the same probability of choosing 1 failure. So there are 4 ways where I could put that failure. So 1/16 times 4, which is, and just for the other people at home here, hard time with fractions here, that's totally fine. We can definitely work on some fractions. 4/16, because that's basically 4/1, right? 4 is 4/1. Multiply across there. I can reduce 4/16 to 1/4. Great. Well, let's use law of total probability. I'm just going to get rid of the 1 there because it doesn't really matter. So 1/16, law of total probability. So law of total probability, if I'm going to apply that here. If I'm going to apply it, that means 1/16 plus 1/4 plus 1/4 plus 1/16. Oh, and I forgot about 2 there. I didn't calculate 2 yet. So I'm going to put just plus x there. I don't know what x is, but I know it's going to all equal to 1. I'm using the law of total probability to calculate how many ways there are to choose 2 successes and 2 failures. That's going to be a little bit bigger of a calculation. All right, so let's see, 1 over 4. We already know that's 4 over 16. That's what we got. First off, I probably didn't have to reduce that. Okay, so 1 plus 4 is 5. 5. Okay, so I have 10 over 16 plus x equals 1. Well, 1 is 16 over 16. That means x must be 6 over 16. Okay, there we have it. That's every probability of rolling, the probability of each and every possible roll. So hopefully you have that down. Now let's say I wanted to use a different approach to calculate these probabilities. And here's the part where the combinatorics come in. We were basically calculating, choosing where to put the failures, where to put the successes. What's the choose function? The choose function, sometimes written in a calculator as, n choose k, is, sometimes symbolizes n choose k like that, or here's the equation. Here's how to calculate it. You have n objects, so you go n factorial divided by k factorial times n minus k, the quantity of that factorial. Okay, hopefully we have that part down. That's k factorial. So k is the number of objects we're choosing. N is the total number of objects we have. Okay. So I want to get those same values. That's how I want to check my work to see that I got the right answer here. All right. So here's my logic here. I have 4 dice. I want to choose none of the, I'll choose successes, okay? Well, the bottom number will be successes. We do that times 1 over 16, or we'll go 1/2 times, so the probability of, of 0 successes, we'll go 0 successes times 4 failures. So we'll make the first number successes. Now this is actually how you calculate combinatorial probabilities. Not in every situation, you're not going to deal with the same probability. In some situations, success, the probability of it might be 1/3, and then failure might be 2/3. A good example of this is roulette. It's not exactly 1/3, or if you put it on a column, it's not going to be exactly. But if you've played roulette, this is similar to what your probability is. All right, and so in this case, it would be n choose k. K being the number of successes. Well, you would go probability of k successes. So it'd be the probability of k successes times the number of those successes. And that'd be multiplied by the probability of failure, which would be simply the total minus the number of successes. Yeah, so if k is the number of successes, that means, the number of successes, the total trials that you have, which is n, minus the number of successes, must equal the number of failures. Well, then this probability is going to be to the n minus k, because we have k number of successes. That's going to be the number of failures. Okay, so this is the equation for, we call it combinatorial probability, or binomial probability is the more common name for this specific example here. So let's finish this out here. All right. So choosing 4, there's one way to choose 4. Well, let's first plug in our formula here. 4 factorial over 0 factorial over 4 minus 0 factorial. Well, I know we define 3 factorial, and here's another identity for us too. 3 factorial as 3 times 2 times 1. That's how we define it. So 1 factorial is going to be 1. 0 factorial, shouldn't that be 0? Here's what factorial calculates itself. Just factorial alone says how many ways are there to list certain objects. And I can go over that in more detail too if you like. How many ways are there to list 0 objects? There's 1 way to list 0 objects. Put this in a calculator and be amazed. It's just a definition for it. There is a calculus way of doing it. If you look up a video on the Riemann zeta function, it will calculate 0 factorial to be as 1 as well. It's just an identity here. It has to do a lot with combinatorics and choosing things and the logic behind that. All right. So we come up with 4 factorial over 1 times, well, 0 minus 4 minus 0 is 4, so times 4 factorial. Well, that's just the same as 4 factorial, which is 1. Oh, but remember we're multiplying that times this here. So it's going to be multiplied by 1 or times 1/2 to the 4th power, or just 1 over 16. Okay, I went a long time on that one, so let's just get down to this, or let's just write down the basic idea of here. So as you've noticed, it's always going to come out to 16. I could go, okay, choosing 1 success and then 3 failures. Either way, I'm multiplying 4 of these. So in this case, however, we can just go times 1 over 16. This will be 4 choose, whoops, not that, that's a different operation there. 4 choose 2 times 1 over 16. This one we have 4 choose 3 times 1 over 16, and 4 choose 4 over 1 over 16. All right. So let's see, 4 choose 1. Okay, so I have 1 factorial, 4 minus 1 factorial. That is 4 factorial over 3 factorial. That's what it simplifies to. Oh, a great thing about factorials is you can simplify these in a kind of an interesting way. You can go 4 times 3 factorial, because that's the same thing as 4 factorial, same as 3 times 2 times 1, right? Well, can't I just write this part as 3 factorial? I can. And why would I? Because the bottom part is 3 factorial. And those would cancel out. And then I have that times, remember I'm multiplying that by 1 over 16. Over 16, that'll come out to 4 over 16, or 1/4. Okay. I'll do these kind of quick. I'm kind of losing memory space here. So choose 2, so 2, then 4 minus 2 factorial, and I'm gonna keep my 1 over 16 on there too. My probability aspect there. So let's see. I have 4. I'm gonna write that as 4 times 3 times 2 factorial. And then I have 2 factorial times, and 4 minus 2 is 2, so times another 2 factorial. The crazy thing is 2 factorial is just 2 times 1, which is just 2. So 2 factorial is 2, and 1 factorial would clearly just be 1. So these are kind of ridiculous to even calculate here. But anyway, I have that. And then, so we know that's just going to be 2. So I'm going to simplify this a little bit here and treat that like, yeah, I'm just going to simplify that. So I have 6 over 16. That would be that probability there. I think that's what we got when we did the other way too, using the law of total probability. Okay. So 4 factorial, choosing 3, 4 minus 3, factorial 1 over 16. Okay. So 4 times, I'm going to just write 3 factorial, because I have a 3 factorial there, and I have 4 minus 3 is 1, so 1 factorial, or just, I can just write 1, or I don't even really have to write it. I can just cancel and say, okay, 4 out of 16. All right, and lastly, and following along great, this will hopefully just kind of hammer home how to do these calculations on our own here. And hopefully we understand why 0 factorial is 1. We can go over kind of other ways to think about that as well. But if it's kind of intuitive for you, great. Definitely look it up on a calculator. It's one of those things that was kind of decided by convention too. Mathematicians sort of came together and said, you know what? There is only one way to list 0, and that's what we use factorials for, is calculating numbers of lists. Okay, so this I'm left with 4, and that's factorial. 4 factorial over 4 factorial over 0 factorial, which is just 1, so I don't really need that. This is just going to cancel out and turn into 1 times 16. So 1 times 16, that's just going to be 1 over 16. So those are all the different probabilities for these dice that we have chosen. Same probabilities sort of go for if you were flipping 4 coins. Do some trials maybe with 4 coins and notice that getting 2 is the most common one that pops up. And even playing this, I can tell you it definitely was the most common one. In fact, whenever we were 2 spaces ahead, it came out to be that. Yeah. But yeah, and I was even calculating percentages too. So as percentages, 1 out of 16, it came out to, if you just divide 1 divided by 16, you get about 6.25%. 1, so a quarter, so that's 25%. And this is the part that kind of got me here, is this ended up being 37.5%. I was expecting like at least some sort of clean number there, but math doesn't have to be clean for it to work out or to be interesting or applicable. Now, if law of total probability says that it should be that every probability of each and every possibility adds up to 1, then these must also add